Imagine a scenario, something that feels, well, a bit futuristic. You're driving a car, a large, modern vehicle.
Okay.
You've been driving for, let's say, 400 kilometers,
Yeah.
a very long journey. You stop on the side of the highway to stretch your legs.
Right.
You walk around to the back of the car, you look at the exhaust pipe.
And usually in that situation, you'd expect
Yeah.
what? Heat, maybe the smell of petrol or diesel fumes.
Exactly. Maybe even a bit of smoke if the engine's been working hard. That's what we're used to.
Mm-hmm.
But in this car, there's no smoke, there's no smell, there's just water.
Clean water.
Clean, clear water dripping out of the tailpipe. In fact, the water is so pure that you could technically catch it in a glass and drink it.
I would probably let it cool down first. It comes out quite hot, but
Yeah.
chemically speaking, yes, it is pure water.
So is this science fiction a magic trick, or is this actual chemistry?
It feels like magic, but it is absolutely real chemistry.
Yeah.
This is the magic of fuel cells.
Yes.
And for our listeners who are tracking their syllabus, we are diving deep into Unit 2.
Electrochemistry.
Unit 2. Okay. Now, we often hear fuel cells described as the holy grail of clean energy. That's a huge title.
It is a massive title.
I mean, we have solar, we have wind, we have lithium batteries. Why does this specific technology get the holy grail status?
It is a big title, but I think it's deserved. It comes down to two main things: efficiency and cleanliness. You see, a standard internal combustion engine, the petrol engine in most cars, it's actually very wasteful. Only about 33% efficient.
Only 33%? That sounds incredibly low.
It is. That means for every 100 rupees of petrol you put in your car, you're effectively wasting 67 rupees.
Wow.
That energy is just lost as heat, friction, noise. But a fuel cell, it can reach efficiencies of up to 60%.
Double.
Double. And the best part, continuous power with zero pollution. No carbon dioxide, no nasty oxides, just that water dripping from the tailpipe. That's a very compelling argument. But let's unpack the name itself, fuel cell. I think for a lot of students, honestly for me too, when we hear cell or battery, we think of the thing in our phone. Is a fuel cell just a fancy battery?
That is the most common misunderstanding, and it's the first thing we need to clear up.
Okay.
It sits somewhere between a battery and an engine. To understand it, I want you to think of a simple comparison. A candle versus a gas stove.
A candle versus a gas stove. Okay, I'm visualizing them now.
Think of a normal battery, like the AA battery in a remote or the one in your mobile. Think of it as a candle. You light it, it burns, gives you energy, but where's the fuel?
The fuel is the wax. It's the candle itself.
Exactly. The fuel is stored inside the device, and as it burns, the wax runs out. Eventually, the candle's gone. It's dead.
Right. So a battery is a storage container that eventually runs empty.
Correct. Now, contrast that with the gas stove in your kitchen. As long as the gas cylinder is full and the pipe is open, does the stove ever die?
No. As long as the gas flows, the flame just keeps burning.
Precisely. The stove doesn't store the fuel inside. The fuel comes from an external source. As long as you feed it fuel, it works continuously. That is a fuel cell.
It's the gas stove of electricity.
That's it?
I love that analogy. It makes it so clear. A battery is a warehouse that empties out. A fuel cell is a converter that just keeps running as long as you supply it.
That is the anchor concept. If you understand that, you've understood the fundamental difference.
So let's try to visualize what this device actually looks like. Listeners, close your eyes for a moment. Unless you're driving, of course.
Yes, please don't do that.
Imagine a device. It's a box. No moving pistons, nothing like that. It has two tubes attached.
One tube is feeding in the fuel. In most common cases, this is hydrogen gas.
And the other tube is feeding in air, or more specifically, oxygen from the air.
Right. And as long as those gases flow in, electricity flows out the other side. There's no charging needed. You don't plug it in. You just feed it gas.
That sounds incredibly simple on the surface. But since this is electrochemistry, we know it's never that simple. There must be something happening to the particles.
Of course. Let's look inside that black box. Inside, we have the standard setup: anode, cathode, and an electrolyte in between.
Okay. Anode, cathode, electrolyte, the usual suspects.
Imagine the hydrogen molecules arriving at the anode. They hit a catalyst, which is usually platinum. Now, platinum is very good at breaking things apart. It forces the hydrogen molecule to oxidize.
Oxidation is loss of electrons. Oil rig.
Exactly. So the hydrogen splits. It separates into hydrogen ions, which are just protons, and it releases electrons.
Okay.
Now, here's the clever part. The electrolyte in the middle is like a very strict security guard. It lets the protons pass through, but it blocks the electrons.
So the protons get a pass to go through the middle, but the electrons are stuck.
They're blocked from taking the shortcut, but they really want to get to the other side to meet the oxygen. So what do? We give them a detour, an external wire.
Ah, and that flow of electrons through the wire. That's our electricity.
That's our electricity. That's the current doing work, turning a motor, lighting a bulb.
And what about the protons that took the shortcut?
The protons, the H+ ions, they arrive at the cathode, and this is where the reunion happens.
Right.
At the cathode, three things meet. The protons from the inside, the electrons coming from the long way around wire, and the oxygen coming from the second tube.
So hydrogen ions plus electrons plus oxygen.
And basic chemistry tells us hydrogen plus oxygen gives you
Water, H2O. That's the only product.
the only product.
That is actually quite elegant. You split hydrogen to force the electrons to do work, and then you just put it back together again as water.
That's the whole mechanism.
Yeah.
Simple, but brilliant.
So if a student is listening and needs a definition for the board exams, something solid, what's the exam-safe definition?
I would define it like this. A fuel cell is an electrochemical cell that continuously converts the chemical energy of a fuel into electrical energy.
The key word there being continuously.
Absolutely. If you miss that word, or you imply reactants are stored inside, you're describing a normal battery. You have to emphasize the external supply.
Talking about this external supply, it brings up that factory analogy we discussed. I think we should break that down.
Let's do it. So imagine the fuel cell is a factory.
Okay. The factory has a loading dock. Trucks come in with raw materials. In this case, trucks carrying hydrogen and oxygen.
Right. Inside the factory, the machinery processes these raw materials. That's our electrochemical reaction.
And then out of the shipping dock comes the product, electricity.
Ah,
And out of the waste pipe, pure water.
perfect. Now, what happens if the trucks stop coming?
The factory stops working.
Does the factory die? Does the
Yeah.
machinery break?
No, it just sits there waiting.
Yeah, exactly. A battery dies,
Mhm.
its internal supply is gone. A fuel cell factory just goes on standby until more supply trucks arrive.
That makes it so clear why you don't recharge a fuel cell car by plugging it in. You just fill up the tank, you send in more trucks.
Precisely. This is why a hydrogen car can refuel in 5 minutes. Just like a petrol car. You're just refilling a storage tank.
There's another way to think about it too, right? The waterfall analogy.
Yes, that's a good one too. A waterfall produces energy as long as the river flows. The power exists because the water is moving. If the river dries up,
The power stops.
exactly. The fuel cell harnesses the flow of fuel.
So why does this technology even exist? I mean, we have combustion, it works, we have batteries. Why did scientists bother with this?
It solves a massive problem. How do you get power from fuel without burning it? You see, burning things, combustion, is inherently dirty,
It's messy.
very messy. Smoke, heat loss, noise. Scientists wanted to bypass the fire stage. And what's interesting is this isn't new technology. A man named William Robert Grove figured out the basics back in 1839.
1839, that is incredibly early.
It is, but it just sat on a shelf for over 100 years. It was a curiosity. We didn't really need it because we had cheap coal and oil.
So what changed?
It wasn't until the 1960s that it found its true calling.
Let me guess. The space race.
The Apollo space program.
Right.
NASA had a huge problem.
Right.
They were sending astronauts to the moon. They needed electricity for everything, but batteries were way too heavy, and you can't just run a petrol generator in a spaceship.
And I'm guessing solar panels weren't efficient enough back then.
Not at all. So they used hydrogen fuel cells. They carried tanks of liquid hydrogen and oxygen, and the cells provided power for the entire journey. But there was a bonus.
The water.
The water.
Mhm.
In space, every kilogram matters. They didn't have to carry huge amounts of drinking water. The fuel cells produced it as a byproduct, and the astronauts actually drank it.
That is just incredible. The astronauts were drinking the exhaust from their own power plant.
It was the perfect little ecosystem for a spaceship.
So we've gone from 1839 to the moon, let's bring it back to Earth, to a hydrogen filling station.
Okay, let's picture this.
You pull up in a car, looks normal, maybe a bit futuristic. You get out, you grab a nozzle, but you're locking it onto a pressurized valve.
You hear that hiss of gas. That's hydrogen, H2, rushing into a high-pressure tank in the car.
Okay, tank is full. 5 minutes, you get in, press the start button. What's happening under the hood?
Deep inside the stack, that's what we call a pile of fuel cells.
Yeah.
The hydrogen rushes into the anode compartment.
Right.
Billions of H2 molecules get that platinum catalyst. They split. H2 becomes 2H+ and 2 electrons.
And here's the movement again. The electrons want to cross, but they're blocked. They have to take the long way around through the wire, they zip through the motor, spin the wheels.
And arrive at the other side. Meanwhile, the protons, the H plus ions, they take the shortcut through the membrane. They meet the electrons on the other side, grab some oxygen from the air intake, and poof.
A water molecule. And the output, we are back to that first image, water dripping from the tailpipe.
Just a quiet drip, 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 no smoke.
It's such a clean mental image, but is it just theoretical? Can a student actually see this happen in a lab?
Oh, absolutely. It's quite a beautiful experiment.
Describe it for us.
Imagine a beaker, some dilute acid. You put in 2 platinum electrodes. Then you just bubble hydrogen gas over one electrode and oxygen gas over the other.
Okay, bubbles on both sides.
You connect a voltmeter between them and you'll see a reading, around 1.23 volts, theoretically. And if you touch the beaker, it gets slightly warm.
Why warm?
Well, the reaction releases energy. Some is electricity, some is heat. Thermodynamics tells us no conversion is ever 100% perfect.
Right. And in the real world, we have actual cars doing this.
Yes, the Toyota Mirai, the Hyundai Nexo. They're the big examples right now.
I've read about the Mirai. The 5-minute refuel time is a huge deal. But here's the counterintuitive part. Here's where I have to play devil's advocate.
Go on.
If these things are 60% efficient, refuel in 5 minutes, and only emit water, why aren't we all driving them? Why are my neighbors buying battery electric cars, not hydrogen cars?
That is the big question. And it brings us to a concept called infrastructure inertia.
Infrastructure inertia. That sounds heavy.
It's a very heavy problem. Think about it. We have petrol stations on every corner. We have electric plugs in every house. The network is built.
But where's your nearest hydrogen station?
Exactly. I have no idea where mine is. Probably hundreds of kilometers away.
So the tech is great, but the network isn't there.
The tech is great. The chemistry is solid. But we don't have the network to store and transport hydrogen yet. It's a classic chicken and egg situation. Nobody buys the cars because there are no stations.
And nobody builds the stations because there are no cars.
Precisely. Plus, storing hydrogen is, well, it's difficult. It's the smallest molecule. It wants to escape. You need very high pressures or very low temperatures. It's expensive.
So for our student listeners, it's important to understand both sides. The science is perfect, but the logistics are the challenge.
Absolutely. Mentioning the engineering challenges shows a complete understanding of the topic.
Speaking of understanding, let's make sure our listeners are ready for the exam. We need those golden rules, the exam-safe clarity lines.
Right. Pen and paper time. These are the points that get you the full marks. I'll go through them slowly.
Let's do it. Rule number 1.
Rule 1. Continuous operation. Fuel cells operate continuously as long as fuel and oxidant are supplied. Do not confuse this with batteries that run out. It's pure supply and demand.
Got it. Continuous supply, continuous power. Rule number 2.
Rule 2. The reaction equation. Keep it simple. 2H2 plus O2 gives 2H2O.
2H2O plus O2, write RO2H2O.
But water is the only product. If you write carbon dioxide, you have lost the marks.
Big red X on the paper if you write CO2. Okay, rule 3.
Rule 3. Voltage limitations. A single cell has a low voltage, usually 0.6 to 1.0 volts. You cannot run a car on 1 volt.
So what do we do?
We connect them in a stack, that means in series, to get usable power. So when you see a diagram, remember, it's just one slice of a very large stack.
Stack them up for power. Got it. And the last one, rule 4.
Rule 4. Thermodynamics. They are not perpetual motion machines. They need external chemical energy to run. They convert energy. They don't create it from nothing.
An important distinction. Physics always applies.
Always.
Okay, we've covered a lot today. From water dripping out of a car to, well, infrastructure challenges. Let's do a quick recap.
Let's summarize.
The core idea. It's the gas stove of electricity. You feed it, and it works.
Right. Unlike the candle or battery, which just burns down and dies.
The visual. The factory. Trucks bring in hydrogen and oxygen.
The factory pumps out electricity and water.
And we connected this to the real world, the Apollo missions, the Toyota Mirai.
And, most importantly, that final takeaway for the exam.
Unlike a battery?
The reactants are outside the cell. That is the anchor concept. If you remember that, you can figure out the rest.
So here's a thought to leave everyone with. We talked about infrastructure inertia, but what if we solve that?
If we crack the code on cheap, green hydrogen distribution.
Exactly. If we could pipe hydrogen into our homes like we do with natural gas today, could your house become its own power plant? Could this technology make the noisy, smoky combustion engine completely extinct?
It's a fascinating thought. The chemistry says yes. The engineering is getting there. It's just a matter of building the world that can support it.
Something to mull over. Understanding fuel cells isn't just about Unit 2. It's about understanding a possible future of green energy.
Absolutely. It's the chemistry of tomorrow happening today.
Thanks for diving in with us. Keep learning, stay curious, and we'll catch you on the next deep dive.
Goodbye, everyone. Happy studying.